In this video, with the help of Bernoulli's equation, we are going to find speed of efflux. To find the speed of efflux, we are going to consider a tank filled with a given liquid, and the liquid is flowing from broader side of the tank to the narrow side. It is an open tank, and this open tank is filled with some liquid. Let us say rho equals to density of the liquid. This tank having two sides, one is the top, another one is the bottom. Both are open. So open top of the tank and open bottom of the tank. The given liquid is entering the tank from large cross section and going out of the tank from small cross section. The material, that is liquid, given liquid, is outflowing from this smaller cross section. So that liquid which is flowing out from this smaller cross section is called efflux. We need to find derivation expression to find speed of efflux. The speed of efflux filled in tank can be derived from Bernoulli's equation. Bernoulli's equation is helpful to find the relationship between the three types of energies when liquid is flowing through a tube of different cross section and at different heights. According to Bernoulli's equation, addition of pressure energy during liquid flow and kinetic energy of liquid flow, of liquid or fluid, it is valid for both liquid and gases. So we use fluids. So kinetic energy of liquid, it can be a gas also. Liquid and gases are called fluids. So kinetic energy of, here we have considered liquid. So kinetic energy of liquid during liquid flow per unit volume and addition of gravitational potential energy is equals to constant. Once again, according to Bernoulli's equation, addition of pressure energy and kinetic energy of liquid which is flowing through the pipe and gravitational potential energy, addition of all these three energies always remains constant during the liquid flow. This equation nothing but called Bernoulli's equation. The speed of efflux flowing out of this tank can be obtained by using Bernoulli's equation. Let A1 be the area of cross section of top surface of tank through which liquids start flowing, and A2 equals to area cross section of orifice. This orifice is nothing but small round shaped hole at the bottom, that is called orifice. So A2 is the area cross section of orifice through which liquid is flowing out. One more important thing, that is the area of cross section of orifice is very much smaller compared to area of cross section of open top of the tank, as the liquid is flowing from top end and going out of this container from the bottom end. So question is, the speed of liquid are the same? Answer is no. The speed of liquid at the top end and bottom end are not same. That is called V1 be the speed of liquid at top open end, that is at A1, and V2 be the speed of liquid at orifice, that is speed of liquid at bottom open end. Let the open top surface at a height h with respect to orifice. That is distance between orifice and the top open surface, that is a free surface, is equals to h. Since top surface is exposed to open atmosphere, therefore the pressure at the top surface is equals to atmospheric pressure, call it P naught. Similarly, even the bottom of the container, that is orifice, even it is exposed to atmospheric pressure, therefore pressure at A2 is also P naught. So rho equal to density of liquid, V1, V2 are the speeds, P naught equals to atmospheric pressure, H equals to height of open surface from orifice. Let us call H1 equals to H and H2 equals to 0. Now let us apply Bernoulli's equation to the liquid flowing through this tank from top to bottom. According to Bernoulli's theorem, the addition of pressure energy, kinetic energy and gravitational potential energy of liquid flowing through a given pipe of different cross section is equals to constant. That is, total energy at top open surface of liquid flow equals to total energy at bottom orifice of liquid flow are equal. So applying Bernoulli's equation for the top surface and to the bottom surface. So for top surface, the Bernoulli's equation is P naught plus half rho V1 square plus rho G H1. H1 nothing but H. So rho G H1 equals to, that is equals to the total energy of bottom surface. For bottom surface, the total energy is P naught plus half rho V2 square plus rho GH. But for the bottom surface, H2 equals to 0 implies rho GH 0 equals to 0. Therefore, the 0 will come here. Now using equation of continuity, that is nothing but A1 V1 equals to A2 V2. This is nothing but called equation of continuity. From this, we can get V1 equals to A2 V2 divided by A1. In Bernoulli's equation, P naught and P naught get cancelled. So we get half rho, and in place of V1, we can write A2 V2 divided by A1 whole square plus rho GH equals to half rho V2 square. Here multiplying and dividing by 2 and taking 1 upon 2 common, rho common. So what is left now? A2 V2 divided by A1 whole square plus 2 GH equals to half rho V2 square, and cancelling half rho both sides. This part can be written as A2 divided by A1 whole square multiplied by V2 square plus twice GH equals to V2 square. Implies keeping twice GH at LHS and taking remaining part to the RHS, that is V2 square minus A2 upon A1 whole square multiplied by V2 square. So twice GH equals to, now taking V2 square common, so we get 1 minus A2 divided by A1 whole square. Now we have to find the expression for V2. Our aim is to find V2, that is the speed of efflux. And we already told that the A2 is very much smaller than A1. Implies A2 1 minus A2 divided by A1. This value is very small, and 1 minus A2 upon A1 whole square. Even this value is more smaller than 1 minus A2 divided by A1. Terms in the bracket being very small, it is neglected. So we get V2 square equals to twice GH. Now taking square root both sides, therefore we get V2 equals to under root of twice GH. V2 is nothing but speed of efflux.